Hello and welcome back to Functions. In today's part 5, I'd like to keep exploring functions, specifically radical ones, basically functions that have a root. However, before we get into that, first I'd like to thank all the nice people that support this channel by liking and subscribing. It really helps massively for me to make more videos for you to enjoy. Now, radical functions are functions that have the form y is equal to the square root of f of x. In this case, f of x is going to be most of the time a linear function, or in other times could be also a quadratic one. Of course, this will immediately tell us something about the domain, because anything that's under a square root cannot be negative. This means that f of x must always be greater or equal to 0. Now, for you mathematicians who know a bit more things, you might start taking the square root of a negative number, which just results in a complex or imaginary number, which is true. However, then a graph wouldn't exist on the real plane because the values aren't real. For those who have no idea what I'm talking about, it's probably for the best for now. And a separate playlist about complex numbers will be made in the future. Continuing with radical functions, for the most basic one, it's y equals to the square root of x. Now the domain is immediately clear. It's simply x that must be greater or equal to 0. However, what about the range? Well, I can immediately tell you that the range is going to be the same. Y equals to or be greater than 0. But you might argue that when we take a square root of a number, it's always going to be plus minus, which is true for numbers, but doesn't really work for radical functions. Let me explain. If you were to graph this radical function square root of x, it would look something like this. Positive x and y values make up this graph. Now, if you say that there are also corresponding negative y values, which means that this graph is now mirrored across the x-axis, and we will also have this bottom part here. You can think of this as a lying parabola. But then this graph is not a function because it does not pass the vertical line test, which I talked about in the introduction video. Drawing this vertical line anywhere will result in crossing our graph twice, hence it is not a function anymore, which is why the range must be limited, hence the range is y greater than or equal to 0. Now, this same logic will work for more complicated radical functions. So let's try working with an example where we'll combine both radical and rational functions, which were covered in the previous two videos. Let's say we have a function given as such, and we have to find the domain and range. We begin with the domain, and there are actually two layers, because in the bottom of the denominator, we have the square root of a quadratic function. Anything under this square root must be greater or equal to 0. However, since this square root is in the denominator of a fraction, we have to take away this equal sign because we cannot divide by 0. Hence, this means that 2x squared minus 3x minus 2 must be greater than 0. So now we're basically solving a quadratic inequality. You should know how to do this, but let's just walk it through. We first find the critical points by equating our quadratic function to 0. You can then solve this using the quadratic formula or using factorization. I personally prefer the factorization method, and I get two zeros, x equals to 2 and x equals to negative 1/2. We then put these zeros on a number line. What we have are 3 different intervals, and we can just pick any value from each of the intervals, plug it back into our quadratic function to see if we get a positive or negative value. Since this is a quadratic function, I know that the intervals will be alternating, meaning plus minus plus minus. Hence, the easiest way to do this will be to probably pick 0, because when we plug that in, what we get is negative 2. So that means in the middle here, we have a minus, so that means we know that on the 2 sides, we're going to have plus and plus. Now, since we require the function to be greater than 0, the side intervals are going to be the domain, meaning x is going to belong to from negative infinity all the way until negative 1/2, which is not included, union another interval from 2, which is also not included, until positive infinity. And here we have found our domain. We can now move on to finding the range, which is going to be more analytical because you have to observe certain key factors. The expression under the square root is always positive in the domain. That means that the square root of 2x squared minus 3x and minus 2 is always going to be greater than 0. As a result, this function f of x is always going to be greater than 0 because we're always dividing by a positive number. Now, 2 things to observe here is as x approaches plus minus infinity, which is actually incorporated in our domain, the function itself is actually going to start approaching 0. As for the other one, as x approaches negative 1/2, or as x approaches the 2 values at the end of our domain, our f of x is actually going to approach positive infinity. This is because as x approaches these 2 critical values, the square root of this expression is going to be smaller and smaller, near 0. And when we divide 1 by this really small number, we're going to get an infinitely large number. Hence, the range is going to be y includes from 0 all the way until positive infinity. And here we have found our range. You will notice that for the range, it's going to be more analytical and has to follow a chain of logic. It also heavily depends on your domain calculation, so please make sure the domain is calculated correctly. For you curious minds, this is approximately what the function looks like on the graph. Alright, so this is it for radical functions. In the next video, I'm going to cover a technique called partial fractions. Once again, it will have something to do with rational functions. So I hope to see you there and have a nice day. Bye.